Hi, and welcome to Module 16 of Lecture 1. In the previous module, we discussed central tendencies, average values of data representing a particular variable. In this module, we're going to talk about variation around those average values. So as we learned last time, right, the mean doesn't perfectly represent all the data points. It's the average value, but around that value, there could be a lot of variation. We measure that variation via deviations, which we calculated last time. Remember, a deviation was the difference between x sub I, which was a particular data point that we took in our data of the variable x, which is some independent variable we have, and we subtract out the mean of that variable x bar. That was the deviation of that point. And we said some deviations were negative if the xi, the data point x sub I, was less than its mean x bar, and some are positive if the xi was greater than x bar. Okay. These deviations tell us how spread out the data are around the mean. How spread out data are is called dispersion. If deviations are overall small, the data are tightly clustered around the mean and we have low dispersion. If the deviations are in general large, data are spread out around the mean and we have high dispersion. To get a sense of what that looks like practically, let's look at some fake data. So here's 6 imaginary state spending on students per month. The mean and the median are pretty close together in this case. And we can calculate deviations and put them on a plot here. So for all 6 states, we see some deviations are negative, some are positive, some are big, some are smaller. Now, what we want here is to get some measure of typical deviations to give us a sense of how dispersed our data are around the mean. We could just add all deviations, right? So on the last column here of this table are all deviations listed from the previous plot, and we could add them up. But if you remember from last time, in the last module, if you add up all deviations, you always get 0. That relates to the definition of the mean. Some will be above, some xi will be above, some will be below, as we said, but the overall average of all deviations must be 0 by the definition of the mean. So, what do we do with that? Well, we have to come up with some other way of getting a sort of average deviation, a typical deviation. So what we do is we get rid of the negative signs by squaring all deviations. So here in the last column, we've squared all deviations, and most of them got much bigger. Now we can take all those squared deviations and add them up. When we do so, we get the sum of squared errors. They're called errors because in this case, x bar is the expected value of x. It's the first pass model of what we would expect the value of x to be if we were to just choose a value of x at random from the population, from the population as a whole. Because of that, any deviation from that first best guess is going to be an error from our model effectively. Once we get better models later on in the course, we'll replace that x bar with a fitted value of the outcome that's better than just x bar and get smaller errors, but for now we'll focus on x bar. But either way, you have this sum of squared deviations is known as the sum of squared errors for that reason. Okay, so what do we do with that? Well, once we've added them all up, we can divide by the number of data points minus 1 to get the sample variance. The sample variance here is represented by s squared. Again, remember this sum, this capital sigma represents a sum, so we're summing over all the data points, and in particular we're summing over all deviations between each data point and the mean. We square that and we divide by n minus 1. Okay. In this case, we have 1874 divided by 5. That gives a sample variance of about 375. And that variance tells us typically how much a data point differs from the mean. It's the second moment of our sample. Now, it's a pretty big number, and often we don't want to work with such big numbers, so we can also take the square root of s squared, the sample variance, to get the sample standard deviation, which we call s. So s is just the same as s squared, but you take the square root of s squared to get s. If the variance was 375 approximately, the standard deviation is approximately 19. So 19 is a number much more in line with the numbers in the actual data, so we can get a sense about how wide the dispersion of the variable is, of our sample is, by using the standard deviation. many standardized tests, for instance, are scaled by choosing a mean and a particular standard deviation to get a particular bell-shaped curve. We'll discuss that a little bit into this course and more later as well, this module and more later as well. Okay, but take a step back for a second to talk about more about population samples, right? All these calculations were done as if we were assuming we're looking at a sample rather than the population itself. So we're drawing a sample from a larger population. That's almost always true, as we said before, when we talked about samples and populations. And that said, there are cases where we do look at populations, right? So if we had all the countries in the world and our unit of analysis was a country, we look at countries and the whole population of countries instead of a sample of countries, potentially. When we do that, we're going to want to divide the sum of squared errors by the population size, right, without the -1. So for our first group of states, if the population is 6, we would divide by 6 instead of 5 if those 6 happen to be the entire population. We refer to the population mean as mu and the population variance as sigma squared. These are lowercase Greek letters. So when we have a population instead of a sample, we call the population mean mu instead of x bar, which is for the sample. And when we have a population variance, we call it sigma squared instead of s squared for the sample variance. These are the first and second moments of the population. The population standard deviation is sigma instead of s for the sample standard deviation. Why am I bringing that up? Because there's a slight difference in how you calculate the population measures than the population statistics than how you calculate the sample statistics. So, and that's because of the degrees of freedom. So consider the following kind of weird example. There are 5 people at a party and there are 5 sandwiches. The first person can pick whatever sandwich they want. The second person now has a constrained choice. They can pick any sandwich they want, but not the one the first person chose. And that's true until the very last person who has no choice at all. That person must eat whatever is left. So 4 of the 5 people have a choice. The 5th person has no choice. What happens is, in the end, we run out of degrees of freedom. The last person has no freedom to choose whatever sandwich that person wants. That's kind of weird. So what's the point of that? The point is, we're doing the same thing here, effectively. We're using the variance and standard deviation of the sample to estimate the true variance and standard deviation of the population. To do that, we're going to assume that the sample mean is equal to the population mean. So if we have a sample of 100 data points, 99 of those values can be anything they want. But the last value, the 100th one, must be fixed at a certain size to make sure the mean is the value we fixed it at. So let me back up. Let me show you again what that means with a calculation. So let's say we fix the mean at 5 in some when we have 5 different values of something. And if 4 values are 2, 7, 9, and 3, then it must be the case that the last value is 4. Because if the last value weren't 4, then we couldn't possibly have a mean of 5, right? So again, we have these 5 data points total. We have 4 particular values, and we fix the mean at 5. Now we know the mean, in order to get a mean of 5, the last value must be 4. Therefore, we don't have 5 free values that we can choose whatever we want from. We have only 4 free values. So only n minus 1 of the data points are actually free. So what we do when we calculate the sample standard deviation is we exclude one value from the calculation. We take the n minus 1 because we've held the population mean to be the sample mean. So we exclude one single value from the calculation. So we divide by the sample size minus 1 instead of the entire population size. When we deal with the population as a whole, we don't need to do this because we're not fixing anything. Right? The population is free to be whatever it wants to be. We actually measure the population mean and don't need to assume that the sample mean is equal to the population mean. So we don't subtract 1. This may seem a very minor point to you, and that's reasonable. So if it's still kind of confusing, as you go on, you'll see, as in this course, we'll see more and more situations in which we will use the notion of degrees of freedom to calculate statistics. And as we see those, I'll point them out. Again, I'll try to remember to point them all out. and harken back to this discussion in which when you have fewer degrees of freedom because you fixed certain values in the sample to effectively be what we're assuming the population is, we will reduce the number of degrees of freedom appropriately in our calculations. So we'll see that later. So just keep that in mind. In this case, just remember if you have a sample you're calculating the standard deviation for, it's n minus 1. If you have a population, it's just n. Okay, so to reiterate, here are the sample formulas. S squared is the sum of squared deviations, the sum of squared errors, over n minus 1. The standard deviation for the sample is the square root of that. Sometimes, potentially confusingly, you will see instead of s squared and s, you will see sigma squared hat and sigma hat. These hats mean the same things as s squared and s in this case. Hats in general are estimates. So our estimate of sigma squared in some sample. They mean the exact same thing. Now, right, the goal of doing all this, by the way, is not just to figure out sort of the descriptive statistics on our variance around in our sample, in our data. It's also to be able to estimate the errors of our sample mean without having to run over and over and over again, right? So what does that mean? This is a very important concept, so I want to make sure this is clear. So when you calculate a sample mean from some sample, that sample mean we're going to assume is the population mean in these calculations of dispersion. However, we know that the sample mean is not necessarily exactly equal to the population mean, right? It's probably different in some way. It depends on how big the sample is. As the sample gets bigger, the population mean should approach the true mean, as we know as well. But in general, any given sample mean will not be exactly equal to the population mean. But it's going to be very important to us to know how different on average that sample mean is from the population mean, because we're going to be comparing these means together, and we want to know how much error is associated with our measurement of the sample mean. So, to calculate the standard error of the sample mean, it's going to equal the standard deviation of the sample, so S, divided by the square root of the sample size. Okay. So as the sample size gets bigger, the error in the standard error of the sample mean gets smaller. And if you have an infinite amount of data, this goes to 0, and you have no error at all in your sample mean calculation. But the smaller the data set, the size of the data set is, the larger will be your error in your sample mean. Again, this will come up a lot more later, so if this part of this module isn't clear totally yet, that's okay. We'll go back to this over and over and over again. The idea to take away right now is that we care about not just the average value of a variable that a variable takes. We care about the dispersion around that average as well, the variance around that average. We can calculate it in this way for a sample, and then we can also calculate using these dispersion calculations the error associated with our measurement of the mean of a sample as compared to the population mean that we really care about. Okay, so let's conclude this module with some pictures of distributions to give you hopefully a better sense of what all these words and calculations mean. So here are two different bell curves, two different normal distributions. In both cases, we've listed the first and second moments of the population associated with that distribution. So the taller curve has a lesser dispersion than the shorter curve, but the exact same mean. So in both cases, the mean here is 52. That's the mu, right? The mean is the center part of this distribution, which is symmetric. In both cases, the same. The lower curve is more spread out and wider. It has higher values further away from the mean and lower values closer to the mean, which means you more often get larger values in this distribution than in this distribution. Well, and smaller values. You more often get values further from the mean in the lower distribution than in the higher distribution if you're drawing things at random. We calculate that using the variance and the standard deviation of the distribution. The higher distribution has a standard deviation of 12. The lower one, twice that at 24. The bigger the standard deviation, the wider is the distribution, and the more likely you are to see randomly values far away from the mean in either direction. So these are important characteristics of distributions. They're not the only ones, though. We can conclude by talking about the third moment, which is more rarely seen in statistics, but can matter as well, called the skew. A skew distribution is not symmetric. More frequent scores end up on one end instead of the other one, and there are two types of skew, positive and negative skew. Here's the normal distribution. The normal distribution is symmetric around this mean. This one here has a mean of 0. So we see is that the normal distribution is bell-shaped. That's why it's called a bell curve sometimes, and symmetric around this mean, and the majority of its values lie close to the mean. A positively skewed distribution has values that trail off far to the right. There are a few scores out here far to the right, but you can actually get quite large values with some small probability in a positively skewed distribution. This is the kind of distribution you often see for wealth given inequality, given economic inequality. Most people are clustered around the mean, but there's a long tail of individuals, some of which will have quite large incomes and quite large wealth. This is the kind of skewed distribution, by the way, that produces situations like we saw in the example in the last module when we saw how the mean can be pulled away by outliers. In this case, the median is down here, but the mean is further to the right than the median because the high values pull the mean to the right away from the sort of central area in this distribution. The opposite side, negative skew, is the opposite. It's when there's values to the left of the mean. And here, the mean is pulled to the left of the median. But it's basically the same thing, just mirrored. Okay. So that covers this. And this covers, now we've covered in lecture 1, both theory and scientific progress and how this all works, and measurement and research design. So this part comprises the setup to the course in a way, but also in a way it's probably the most important part of the class in that it gives you an insight, hopefully, into how to go about raising questions scientifically and then answering those questions. If you don't have good research design, if you don't have good solid theory, everything we do later in the class is not that important. It's not going to really tell you much about how the world works. So this is in some sense the more important of all the material in this course. In the next, which is the last module of this lecture, I'm going to go through a couple of short problems just to give you a sense of how to calculate and some practice in calculating these means and standard deviations and so on. And then there's also a problem set online on this course's website that you can do if you want extra practice. In the next lecture, we're moving on to causal inference, which we'll do for the rest of the course. Thank you very much.